Hi, my name is Tassia Ferreira, and today I will be talking about my work with cosmic shear covariance matrix comparison. So let me start by giving some motivation for the work I'll be presenting here. Covariance matrices are among the most difficult pieces of end-to-end cosmological analysis. We say that because they're very hard to obtain and very computationally expensive. It takes a long time to calculate them, and as we look ahead for future surveys like LSST, DESI, or Euclid, when data vectors will become increasingly larger, the number of elements in the covariance matrix will grow quadratically, making them even bigger and more difficult to analyze. A simpler method of analyzing these matrices is to use compression schemes capable of reducing their size while maintaining the relevant information for comparison and also for obtaining parameter constraints. Let me now describe the observable we are using, which is cosmic shear. So we have this picture here to describe the lensing. The angles are very exaggerated to allow for easier comprehension. However, since cosmic shear is in the weak lensing regime, the angles will actually be very small. What this picture is showing is how light is bent by the large-scale structures as it travels to us from a distant galaxy. The distortion of the background galaxy is used to map and characterize properties of the large-scale structure and give us information about how the dark matter is distributed in the universe. The important quantity here is what we call the magnification matrix, which is the partial derivative of the angle beta with respect to the angle theta. The magnification relates the convergence and the shear components of the distorted image. So the observed image is changed by two effects. The convergence relates to an increase in the size of the image, and the shear describes the distortion of the image with respect to a privileged direction. What we observe is a combination of both of these effects, but since the shear is more apparent, this is going to be the important observable. The shear and convergence of just one galaxy won't be useful for probing this distortion. Instead, we look at the correlation between pairs of galaxies. This picture shows more or less what this correlation looks like. The T subscript describes the tangential component. And here we have the cross component, which is basically at an angle to the line of sight. The observable that we're interested in, the cosmic shear, is represented by psi, which is the sum of the correlation of the two components. The power spectrum, represented by this letter P, is the Fourier transform of the correlation function. This is the quantity that will give us information about the components of the universe. Inside this integral here, we see terms related to the density contrast, which is this delta. And inside this Q function, we have terms relating to the matter density of the universe, represented by omega m, the Hubble parameter, which is this H naught, and also the redshift dependence, which is represented by the scale factor A. So let's move on to the data used for this analysis. We take data from two different surveys. The first one is from the Dark Energy Survey Year 1. It contains 227 data points after some scale cuts, which are represented by these gray regions here. These points are divided into 4 tomographic redshift beams, which are seeing the more colorful plot, and these are further divided into 20 angular bins. The model we use consists of 16 parameters, where 6 are cosmological, 2 are astrophysical, which are related to the intrinsic alignment of galaxies, and we have 8 systematic ones. The second data set is taken from the Kilodegree Survey 1000, or KIDS 1000 for short. Again, this is only for cosmic shear. So we have 235 data points divided into 5 tomographic redshift bins, and then further divided into 9 angular bins. For this set, we have 13 parameters with 5 cosmological ones, 2 astrophysical, and 6 systematics. We use three covariance matrices for this analysis. The first is the DES one, which was generated by a code called Cosmology. The Gaussian covariance one is obtained for DES-like survey, and differs from the original DES one in two ways. The code used to generate this covariance was not Cosmology, but rather the one that the kids' collaboration used for their covariances. We also only take the Gaussian part of the covariance matrix. These differences are introduced on purpose to allow for measurable differences between the constraints obtained for the Gaussian covariance and for the DES one. Finally, the third covariance matrix that we use is the one that was used in the KIDS 1000 analysis. This matrix is not going to be used here for matrix comparison or parameter estimation comparison. We'll only be using it to test our compression schemes. Here we can see the differences in the parameter constraints when using the two different covariance matrices, DES and the Gaussian one. We see that for the omega matrix, there's not much difference, but there is measurable difference for the S8 parameter and for the intrinsic alignment amplitude. So these differences are going to be crucial for testing our covariance matrix comparison methods. Let's move on to the compression and transformation methods that we use. To compress both the data and the covariance matrix, we use the massively optimized parameter estimation and data compression algorithm, or MOPED for short. It compresses the data vector down to the same dimensionality as the number of free parameters. It does the same with the covariance matrix. So basically, for the DES one, for example, it takes a 227 by 227 covariance matrix and shrinks it down to a 16 by 16 one. It's a massive compression because just 16 by 16 is just the number of free parameters. So you could have a 1000 by 1000 covariance matrix, and it should shrink down to the 16 by 16 one. Right, so, the weighting vector is chosen in such a way as to maximize the Fisher information matrix. The scheme is able to provide us with a lossless compression in the sense that no information is lost. The results here speak for themselves with these two superimposed curves. This plot is comparing constraints with the original 227 by 227 DES covariance matrix and those obtained for the 16 by 16 one. They're basically indistinguishable. On the other hand, if we look at the comparison between individual elements of the covariance matrix, this also becomes much easier. Instead of having to look at the large number of elements here, where it's unclear which regions we should be worried about, we now need to care about only a small subset of them. So the problem with the compression scheme is that it's not possible to return to the original covariance matrix once you've reduced its size. However, there are situations when this could be useful. With that in mind, we extend the compression to an invertible transformation. We take the original compression scheme described by this tiny b, and we introduce the matrix U, capable of producing a transformed covariance matrix, where the C1 block here is the same as the one in the compressed case. So it's going to be for the DES covariance matrix, a 16 by 16 C1 block, where the whole matrix is a 227 by 227. These two diagonal blocks are 0, and this third block, C3, is completely irrelevant for parameter constraints. So here we're testing the importance of the block C3 by performing all kinds of modifications to it. And all results point to it being irrelevant for the parameter constraints. Some of these tests were done on the DES covariance matrix, that's these two, by introducing various perturbations to it. And so a 5, 10, and 50% error to its elements while keeping it positive definite. And we don't see a lot of difference to these constraints. For tests on the KIDS covariance matrix, we were a bit more dramatic and simply replaced C1 with the identity matrix. Also, there's not much difference between the constraints. In terms of information, the transform matrix is the same as the original ones, but with a much smaller number of relevant elements. Now for this final part, I will be talking about the covariance matrix comparison that we developed based on these methods. Since all that really matters is the MOPED compressed matrix, this is what we will be using for the comparison. We therefore start by performing a compression on the covariance matrices that we want to analyze. So here C-base and C-test are just the two different matrices that we're comparing. In this example, it will be the DS original one and the Gaussian covariance. The analysis is then divided into two parts. We're interested in differences in the diagonal elements and in the independent elements of the correlation matrix. The whole algorithm is based on a Monte Carlo analysis. We start by creating a mock sample, for example, of the diagonal elements with M components, where M is the step relating to the Monte Carlo process. These mocks are created by perturbing the original diagonal elements by some error delta. The perturbed value is then given by this formula down here. Since this is all squared, we don't have to worry about negative numbers coming up. In the case of the correlation elements, we have to worry about keeping the results between -1 and 1. We therefore use the hyperbolic tangent function, also corrected for the Jacobian. This corrects for any hard cuts we would have to make, and always for an easier translation of the perturbation to the perturbed value. So the perturbation will fall around here, and then the value that we observe is on this line here, on the orange line. Once the mock samples are given for a given perturbation have been generated, we compute the sample covariance matrix S. The fiducial chi-squared is obtained in the usual way as described here. Notice that here we are using the mock sample and what we are calling the base covariance matrix. We then produce a new chi-square, this time comparing the elements of the two matrices that we're actually interested in. This is then iterated until the algorithm finds the perturbation delta, such that this new chi-square is the best fit value of the fiducial chi-square shown in the previous slide. We use this procedure to create a distribution for the values associated to the differences between the elements of the two covariance matrices that we're comparing. Our results are summarized in this plot, which we can then compare to the differences in the parameter constraints of the two different matrices. So we see here an error associated to the diagonal elements and the error associated to the correlation to the elements of the correlation matrix. So we find that the mean values of the parameters of the 16 parameters change on average by about 8%, and that the constraints are about 2.6% larger. This is, of course, an incredible agreement with what we found using our method, which was a difference of 2.6 for the diagonal elements and 7.8 for the elements of the correlation matrix. So to conclude, I want to say that this comparison is useful because it eliminates the need for full cosmological analysis in order to compare the differences in parameter constraints. Our method is computationally faster and deals only with the elements that are actually relevant for parameter estimation.